Today we'll compare the means of two samples using confidence intervals and hypothesis test. Should you buy generic rather than brand name batteries? A stat student wanted to test the battery life. To estimate the difference in mean lifetimes, he kept a battery-powered CD continuously playing the same CD with the volume control fixed at 5 and measured the time until no more music was heard through the headphones. He used 6 sets of AA alkaline batteries, 1 a well-known brand name and 2 generic. He measured the time in minutes until the sound stopped. So notice we have our brand name lifetimes in minutes and our generics listed. So to see a display of the two groups, let's start by comparing the box plots. Now, you don't necessarily have to do box plots. You could do 2 histograms, as long as they're on the same scale. You could do a back-to-back stem and leaf plot. Those are other options as well. But according to our graphic display with the 2 comparative box plots, it looks like the generic batteries lasted longer and are more consistent. When we are comparing 2 means, it's really not that much different from comparing 2 proportions. In our battery example, the population model parameter of interest is the difference between the mean battery lifetimes, mu sub 1 minus mu sub 2. The statistic of interest is the difference of the 2 observed means. That would be x bar 1 minus x bar 2. Remember, for independent random variables, the variance of their difference is the sum of their variances. So to find the standard deviation of the difference between 2 independent sample means is as follows. Now, these 2 formulas are listed on page 2 of your formula packets, just so you know. And because we don't know the true standard deviations, we estimate the standard error. Remember, we estimate it using the sample standard deviations. In our next example, a potato chip manufacturer buys potatoes from 2 different suppliers, Camberley Fields and Ryder Wood Farms. The weights of potatoes from Camberley Fields are approximately normally distributed, that's important, with a mean of 180 grams and standard deviation of 30 grams. The weights of potatoes from Ryder Wood Farms are approximately normally distributed with a mean of 175 grams and a standard deviation of 25 grams. When shipments arrive at the factory, inspectors randomly select a sample of 20 potatoes from each shipment and weigh them. Let x bar 1 minus x bar 2 be the difference in the sample mean weight of the potatoes from the 2 suppliers. What is the shape of the sampling distribution? X bar sub 1 minus x bar sub 2. Because our question already states that both farms are approximately normal, that's what we're going to say. To find the mean of the sampling distribution, all we're going to do is we're going to subtract the mean from Camberley Fields from the mean of Ryder Wood Farms, and we do get 5 grams. And to find the standard deviation of the sampling distribution, we're going to take the square root of 30 squared divided by 20 plus 25 divided by 20 and then square root all of that. We do get approximately 8.732 grams. So the confidence interval we will build is called a 2-sample t interval. It is in the test function in your calculator if you want to use the calculator. 2-sample t interval, where we take the difference of the 2 means plus or minus the margin of error. If you've forgotten what margin of error is, remember it's the critical value times the standard error of the differences. Now, to find the t star of the difference of 2 means is a very complex formula. So you could use what's called the conservative approach if you like using the chart, and you would take one of the 2 samples and use that degree of freedom. Otherwise, you can just run the interval or test in the calculator and it will give you the degrees of freedom. The corresponding hypothesis test is called a 2-sample t-test. When the conditions are met, the sampling distribution of the standardized sample difference between the means of 2 independent groups is as follows. And remember, I never really memorize formulas because I always remember statistic minus the null divided by the standard error of the sample. And it can be modeled by a student's t-model with a number of degrees of freedom found with that special formula. We estimate the standard error as this. Okay, so ta-da. For assumptions and conditions, remember you don't have to state the independence assumption. I would primarily focus on this randomization piece, this 10% piece, and the nearly normal piece. But we have to make sure that data from each group must be drawn independently and at random or generated by a randomized comparative experiment. So remember, for surveys, is the data a representative sample? For experiments, was the experiment randomized? 10%, I only check if there's a very small population or very big sample. I always check it. There are some textbooks that will give you a clue of when to not check it, but I just am always in a habit of checking it. And then nearly normal condition, for both groups, samples of less than 15, I would draw a graphic display. Again, that could be a stem and leaf plot, a dot plot, or a histogram, or a box plot, okay? And remember, if your sample is above 30, the central limit theorem takes over, and we say the sample's distribution is approximately normal. Independent groups assumption, two groups we're comparing must be independent of one another, so you have to think of how the data was collected for this. Back to our battery example, if we look at the box plot, the generic batteries seem to have lasted about 20 minutes longer than the brand name batteries. Before we change our buying habits, what should we expect to happen with the next batteries we buy? How much longer might the generic batteries last? We have the measurements of the batteries. We're going to find a 95% confidence interval to contain the true difference, mu sub g minus mu sub b between the mean lifetime of the generic AA batteries and the mean lifetime of the brand name batteries. Okay, so we have our table and we have our picture. Let's go through our 4 steps. So remember our state step, this is where we state the parameter we want to estimate and the confidence level. So our mu sub g is the mean lifetime of the generic AA batteries in minutes. Our mu sub b is the mean lifetime of the brand name AA batteries in minutes. And for our planned step, we want to do a 2-sample t interval with 95% confidence. Now for our conditions, the batteries are selected at random, but it's not an SRS, should be representative. We know the batteries are packaged together, they may not be independent. A stronger test would be to repeat the study with several different packs. For independent groups assumption, batteries are from 2 different companies in separate packages. They should be independent. And nearly normal, the samples are small, but if we look at our constructed histograms, they look unimodal and fairly symmetric. So we're okay there. Now, primarily you want to make sure you are doing this nearly normal condition, this randomization. Now, notice they didn't do 10%. Well, the reason why they didn't do 10% is the population of the batteries is so large, it's almost silly for us to write that down. I would still get into a habit of writing it down, let's be real. Next, our do step. If our calculations are met, we're going to perform the calculations. On the previous slide, we were given the table of the data. So what we're going to do is we're going to enter that data. List 1, we're going to put the generic battery lifetimes, and for list 2, we're going to put the brand name. When I run my 2 variable stats, notice my n sub b, meaning my brand name is 6. My x bar sub b is 187.433, and my s sub b is 14.611. N sub g is also 6, and x bar sub g is 206.017, and the standard deviation of the generic, 10.302. Now, our critical value, remember, is going to be weird. If I run the interval in my calculator, it's going to give me a degrees of freedom of approximately 8.986 with a critical value of 2.263. However, I can use the conservative approach and use 5 as my degrees of freedom at 95% confidence, and you should get this 2.571. You can do that on the AP exam and be okay. A lot of students would rather just type it into their calculator. This is what it would look like if I were to do the interval by formula. You can run a 2-sample t interval in your calculator if you would like to. Last but not least for this example is our conclude step. So we are 95% confident that the true mean amount of time generic batteries outlast brand name batteries is between 2.1 minutes and 35.1 minutes. If generic batteries are cheaper, there seems to be little reason not to use them. Okay, so because our confidence interval was entirely positive, we can say that they lasted longer, right? We have evidence to suggest that generic batteries last longer. In our last example, Mr. Lucklow's class performed an experiment to investigate whether drinking a caffeinated beverage would increase pulse rates. 20 students in the class volunteered to take part in the experiment. All of the students measured their initial pulse rates. Then Mr. Lucklow randomly assigned the students into 2 groups of 10. Each student in the first group drank 12 ounces of cola with caffeine. Each student in the second group drank 12 ounces of caffeine-free cola. All students then measured their pulse rates again. The table measures the change in the pulse rate for the students in both groups. And notice we have our table and we're already are given the mean change. Do these data give convincing evidence at the 1% significance level that drinking caffeine increases pulse rates on average? Remember, our first step is the state step. We're going to state the hypotheses and what you want to test and define the parameters. So we're going to say mu sub c is the true mean change in pulse rates for students like these who drink 12 ounces of cola with caffeine, and mu sub n is the true mean change in pulse rates for students like these who drink 12 ounces of cola without caffeine. Now, remember in our null, we always assume there's no difference. So our null is mu sub c minus mu sub n is 0. And if I think in the story that drinking a caffeinated beverage would increase pulse rates, we're going to use a greater than sign for our alternative. So our plan is that we want a 2-sample t-test, and now for our inference procedures. We know that the teacher randomly assigned the students to 2 treatment groups, and 20 should be less than 10% of all students. For our large enough step, what we have to do is we have to actually look at a graphical display. Now, you could do a back-to-back stem plot, you could do parallel box plots, you could do 2 histograms as long as they're on the same scale. So if we were to do 2 parallel box plots, notice that our box plots, the sample sizes are small, but the box plots do not show any outliers or strongly skewed data. Now we're ready for our do step. If our conditions are met, we're going to perform the calculations. Because we were given the data, we're going to run our 2 variable statistics. And we already knew the mean for caffeinated and the mean for non-caffeinated that was provided in the table. The standard deviation for caffeinated was 2.670, and the standard deviation for non-caffeinated, 2.625. Now we're going to set up and run our t-statistic. Okay, I'm going to take the difference of our 2 means, and remember, we're going to do 3.2 minus 2 and minus the null, which is 0, divided by our standard error. And we should get something approximately about 1.01. I can sketch that picture, and then I can use my chart to find the p-value. So if I take the conservative approach, 10 minus 1 is 9 degrees of freedom. And we know p is between the t-value 1.01 and is less than 10%. If I look at the top of my table B in my packet. So I go down to degrees of freedom 9, and I keep looking for the value that's closest to my test statistic 1.01. And actually, I get it to be 20%. So it must be the old chart before College Board revised. If I'm using my calculator, notice because my data is already typed in, I run a 2-sample t-test with the appropriate information. Notice we get almost the same t-value, and a p-value is still greater than 10%, and we have all of our sample stats. Last but not least is our conclude. So since our p-value is high, 0.163 is greater than 0.01, we fail to reject the null. We do not have sufficient evidence to suggest drinking 12 ounces of caffeinated cola increases pulse rates for students like these on average. The end. Hooray! Practice time.